20 gazillion options. Okay, the record is on. I just double check, make sure it's recording. And then we can get back to the notes here. All right, so last time we started to talk about resolution, and I changed the notes. I didn't change it, I added to it a little bit, just so that we have a little bit more connection from resolution to normal form, and then to propositional calculus to normal form, and then to resolution. So what we're gonna do today is to kind of go back to normal form a little bit. And first of all, we want to kind of revisit what is CNF, conjunctive normal form, which is something that we introduced last Wednesday. And then we'll try to connect all of these things together, because the one thing that I hate about certain textbooks is they talk about all the concepts, but they never really kind of combine all the concepts and say, okay, this is how they all relate and become useful. So I would try my best, to kind of make sure that, I explain why we are talking about normal forms, how does it have anything to do with propositional calculus, and how these two combine and make resolution really useful. Okay, so these concepts are all related. They're basically pieces of the same puzzle. Okay, so we talked about conjunctive normal form the other day. There are two basic definitions of what is CNF. Okay, I hope you guys still remember what the definition of CNF, conjunctive normal form. How many people still have a vague recall of what it is? Okay, go ahead. Do you want to?
Basically, you go and make it X. So you turn something into something that looks like a bunch of statements that you just add together, and inside those AND statements are ORs.
Yes, and inside the ORs are?
I'm not sure what you mean.
Okay, so we can look at it the other way around as well. Okay, so this is one way to look at it. A single variable is a CNF by itself. Okay, the negation of a single variable is a CNF. So by definition, okay, I know it sounds really awkward because where's the conjunction of a single variable? You can always say and true, okay? Then it becomes CNF, okay? So instead of using and one or and true, all the time, we just say, okay, let's just count a single variable as a CNF. And the negation of a single variable, like not P, not Q, not R, those are also considered as CNF. A disjunction of single variables and negation of variables is a CNF. So this part is kind of contradictory. Let me see if I can adjust the screen. It only has on off. It doesn't give me a auto image. There we go. Let me see if that helps. Yep, there we go. So the third sentence seems kind of contradictory, because it says a disjunction, which is an OR, that involves only variables and negations of variables is also considered a CNF. But this is the largest building block of a CNF. Okay, so then the next one says a conjunction of CNFs is a CNF, which is kind of recursive, but it is also the most important part of it, because now you can chain individual CNFs into a huge CNF. Are we doing okay so far with this description of what is a CNF? Okay, so let me just give you an example here. Okay, so let's say P, Q, R, and S are variables. Okay, in other words, in the alpha set, I define these specific letters to be variables. So in this case, P by itself is a CNF because it is a single variable. I can say not Q. Okay, I'm borrowing the not symbol from C, so I don't have to type as much. So not Q is a CNF because it is the negation of a variable. So now I can say P or, okay, I'm going to use a regular or here. Not Q or R is a CNF because it is a disjunction where the individual components are either variables or the negation of a variable. So it is also a CNF. So now I can say, hey, if all of those things are CNF, if I do a big, huge conjunction of all of those things that are known to be CNFs, the end result is a CNF. So I can say P and not Q and P or not Q or R, that is a CNF as well. Now in this case, somebody may complain and say, but Tack, that is kind of redundant because we don't need all this stuff here. That's not the point. The point is what is considered a CNF. Are we okay so far with what is a CNF and how we can define how the definition works in this case? It's all good? Okay. All right. Okay. So the next question, if I just kind of go back to my notes here, the next question is, can we convert any well-formed formula that we have talked about so far into a CNF? That's the question. And the answer is yes, okay, which is kind of surprising in one way and not so surprising in another way. So if you give me any well-formed formula that is a Boolean expression, I can turn that into a CNF. Are we okay with that idea? Just the idea, not the mechanism of doing it, but just the concept that any well-formed formula can be converted into a CNF. Is that okay so far, or are there any questions about that? No questions, so I'm going to assume that that's okay. Okay. All right. So this part of my notes, can any formula transform into a normal form, is really just giving you all the tools that you need in order to kind of convert any Boolean expression into a CNF. So right here, it says, any well-formed formula with only one single variable. Well, I really should have written it in a different way. A well-formed formula that is a single variable is a CNF. A well-formed formula that is a single negative variable is a CNF. We talked about that already. A well-formed formula that is a disjunction of variables and negative variables is a CNF. We talked about that just a few minutes ago as well. So this is the part where it gets kind of recursive, because it says if phi is a CNF and psi is a CNF, then the conjunction of those two is a CNF. Okay, that part we talked about already. So now the question is, what if we have a disjunction instead of a conjunction? What if psi is phi is a CNF and psi is a CNF, but then we have a disjunction of those two? If you have a disjunction of those two, then you can use the distributive law so that you can just distribute everything and then it becomes conjunction again. So are there any questions about the distributive law in Boolean algebra? If this is what you're given with, then it is the same thing as re-expressing it as this one here. Are there any questions about this part? Because this is one kind of useful tool where you are given two CNFs, but there's a disjunction between the CNFs. So you basically just apply the distributive law, then becomes a big, huge, CNF again. This one is counterintuitive. Okay, this one, because in arithmetics, the distributive law only works in one way, but in Boolean algebra, it works in both ways. Let me explain what I mean by that. Okay, so let's deal with arithmetic first. We are familiar with this one, right? Any surprises here? Hopefully not. Okay, but in arithmetic, this doesn't work. Okay, if I have a plus bc, and I cannot convert this into a plus b times a plus c. Does not work in normal algebra. Is that okay? Does everybody agree that in algebra, distribution only works in one way but not the other? But in Boolean algebra, it works in both directions. Okay, so in Boolean algebra, which is an algebra system on its own, but it is in Boolean algebra, A and B or C, okay, this is the easy one. We can re-express this as A and B or A and C. Okay, and the way we can prove that this works is just by using a truth table. It's really easy to prove. And this one works, it works, but it doesn't help us because it doesn't convert a non-CNF into a CNF. Well, in a way it does because, when you have this on one side, if you start with this, it will turn it into a CNF like this. But the other one is also useful. The other one is A or, and then we have B and C on the other side. This one works too. So it becomes A or B and A or C. So in Boolean algebra, both of these work. Are there any questions about these two distributive rules in Boolean algebra? You guys are supposed to say, I don't believe it, show it, prove it to me. Okay?
Do that in your head, though. You can convince yourself in your head, though.
Well, you can, but you can also kind of more formally do this using a truth table. So this is exactly what I'm going to do is with a truth table. So I'm showing you guys a skill that is going to be useful because with Boolean algebra, a lot of times you can use a truth table to show that two expressions are truly equivalent. So we got 0, 0, 0, 0, 1, 1, 1, 1, and then we got 0, 0. I should have used a spreadsheet to do it because then I can just copy and paste a lot of this stuff. It's okay. 0, 1, 0, 1, 0, 1, 0, 1. There we go. Okay. All right, so anything that starts with A and A is true, I know the entire expression is true already because it is a disjunction. So I can just put all the ones here, just like that. And if A starts with a 0, then I have to look at B and C, because in the case of the first 4 rows, A is false already. So the only way to make the entire thing true is B and C. So I need B, C both to be 1 for the entire thing to be 1. So for all of the other cases, the entire expression is false. Are there any questions about the truth table up to this point? Questions? This is all good? So now I'll work on the last column of the truth table, which is basically this whole thing. So at first, it might take you a little bit of time to figure out, okay, how do we compute this? A is false, B is false, C is also false. In this case, A or B is false, A or C is false as well, and then false and false is false. In this case, we also have a false because even though A or C is true, the first one is false, so we have false and true, which is also false. This one is the flip side of that. A or B is true, but A or C is false, so once again we have true and false, which is false. Over here, we have B, C both being true, so A or B is true, A or C is true as well. True and true is true. And then over here, because A is true, so that means A or B is guaranteed to be true. A or C is guaranteed to be true as well. So for all these 4 rows, we are guaranteed to have true and true, just because A is true. So we have true, 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 true in this case. There we go. So in the end, we can see that these 2 columns are exactly the same, which means even without using any other way, you should be able to convince yourself that these 2 expressions. Let me highlight the expressions here. This expression and this expression are truly equivalent in Boolean algebra. Okay, any questions about this part? No questions? Okay. All right. So that is this portion of the note here. So the next one is if phi is a CNF, then the negation of phi can be transformed into a CNF as follows. There are 3 separate cases. If phi is already a single variable, nothing to do about it. Nothing to do because the negation of phi is already a CNF as well. The same thing applies when phi is the negation of a single variable. Then we have a double negation of a single variable, which boils down to just a single variable, which by definition is also a CNF. If phi is a disjunction, okay, if phi is broken up into psi or rho, then we can apply De Morgan's law. So De Morgan's law basically say, the negation of a disjunction, it becomes a conjunction of negation applied to the individual components. So now we have, the overall form of a CNF. So the next question is, what if the negation of psi? What if psi is a CNF and then the negation of that doesn't fall into the easy cases? Reapply this rule. Okay, that's the whole point, is reapply this rule until you boil everything down to CNF. Okay, the next one is what if phi, the thing that we are trying to negate, is a conjunction? Well, then you apply De Morgan's law, so it becomes, so you apply De Morgan's law, so the negation of psi and rho becomes the negation of psi or the negation of rho. So what do we do here? Well, since the last operation is an or, and we have a way to do with or, don't we? Right here, okay? And so the first thing you need to do is to convert not psi into its own CNF, convert not rho into its own CNF, then you go back to this rule and say, okay, now we have a CNF or a CNF, and then you can just use the distributive law to handle that one. In other words, these rules, each one does not solve the entire problem, because a lot of times after the application of one, you end up having to apply some of the other rules. But by reapplying the rules over and over again, you should be able to convert any Boolean expression into a CNF. Is that okay so far with this? Okay, how does this have anything to do with propositional logic that we have discussed up to this point?
Resolutions have to be in CNF?
Well, I haven't talked about resolution today yet, okay? But what does this have anything to do with propositional logic up to this point? So can someone remind me how I defined the propositional calculus system from the previous week? Okay, let's talk about alpha first. What did I put into alpha?
Variables.
The variables. Okay, we start with constants, okay? False, true are constants. And then we start with some variables, P, Q, R, P, Q, R. And then we have some Greek letters to represent schematas. So we have phi, psi, rho. Okay, so this is a typical way to define alpha for propositional calculus. How did I define omega? Those are the connectives. Those are the quote-unquote operators. So what do we have as operators? Well, we have 1 in omega 1, okay, union omega 2. So omega 1 would only consist of operators that require one operand, and which one only requires one operand in Boolean algebra?
Negation.
Negation, all right. So we have negation here, and then what about omega 2? There are a few. So we have the usual, we have conjunction, we have disjunction, and then we have implication, which can be expressed as a disjunction and a negation, but it's conventional that we want to use it on its own. And then we also have equivalent to. So these are the connectives. Are we doing okay so far? But at this point, with only alpha and omega, we can only define what is considered a well-formed formula, but those formulas do not have any meanings. We don't know what is true and what is false. So that's why we need iota. You guys remember iota? So iota are the constants, or the things that are by definition true. So the things that are by definition true is 1 itself, okay, without question, because 1 is representing true. But we also know the negation of false is also true. Without this, without not 0 in iota, we would not be able to define what is negation. This is how we define negation. The negation of false is true. Okay. What else? We also know that 1 and 1 is true, right? We know that 0 or 1 is true. We know 1 or 0 is true. We know 1 or 1 is true, and so on. So everything that involves constants that is true, we want to put it into we want to put that into iota. Okay. And we're missing one more set here, because sigma, okay, sigma represents the transformation or inference rules. Okay, I'm going to put it up over here because the podium is in the way. So sigma represents all the transformations, which means each rule inside sigma has two components. On one side, you have a set of well-formed formula. On the other side, you have a consequent well-formed formula, which is the result of that. Okay, we looked at some kind of interesting ones where it's an empty set on one side, and then we use this symbol to mean inference or infer. And then the other side, we can just say, oh, from knowing nothing, I can already deduce that any schemata or the negation of that schemata has to be true. Do you remember this stuff? And then we also throw in a lot of stuff where it is bidirectional, to represent all the rules that we use in Boolean algebra. So it's basically just a whole bunch of rules like this in sigma. So in sigma, we have individual elements being inference rules. Are we okay so far with all this stuff here? I'll just give you another one that is kind of obvious, but it is also going to be useful in today's lecture. So I can also say that if in the set, okay, of known to be true well-formed formula, if psi is known to be true and phi is known to be true, okay, in the system of propositional calculus, then you can also infer that the conjunction of these two is also true. This one is kind of by definition, because if you can find psi and phi inside the system, that means they're both true to begin with. So by using these transformation rules, okay, we are gradually and slowly expanding the number of well-formed formula, and hopefully we'll find the theorem that we want to prove to be in the set of true well-formed formula in a system like this. That's the whole idea of the propositional calculus system, is to prove theorems. Are we doing okay so far with all this stuff here? Yes? Okay. But this is particularly important. What is that saying? How does that connect to the concept that we were just talking about 15 minutes ago? What does this have anything to do with C and F? Everything that we can derive can be combined into a single gigantic CNF. Okay? So that's the connection, okay? This part here, let me just kind of highlight this part here. This is the connection between general propositional calculus, which is all this stuff here, this is the connection to CNF, conjunctive normal form. Is that okay? Does everybody understand the connection between propositional logic and CNF? Okay, yep, go ahead.
I thought that was a Z. I thought sigma was a Z.
Sigma is?
Yeah, I remember going over the propositional calculus and you had it as a Z and you called it zeta. I don't know, I might have heard that somewhere else.
That could be the case. Maybe I used the wrong symbol here. Wouldn't be the first time I used the wrong symbol. I think it's zeta. You're correct. So I was inconsistent in my own notes. This is supposed to be zeta.
It says it here, but in the
previous note I used zeta.
Right.
Yep, I know. I remember now. So this is supposed to be zeta, but it is still the set of transformations. That's the important part.
Okay.
Yep.
Just the symbol's different, but everything else is the same.
Yeah, I just misused the Greek letter.
Okay.
Yep. But the connection is still the important part. Is how the CNF relate to propositional logic. Is in propositional logic, we are trying to apply all those rules in zeta, the transformation rules or the inference rules, to come up with consequent well-formed formula, and we're just trying to come up with the well-formed formula that is representing the theorem that we're trying to prove. So that's how we're trying to prove theorems in propositional logic. The problem with this approach is we have so many operators, so many connectives, and they can, and we have connectives, excuse me, we have inference rules like this, okay? So we can just come up with random new stuff and put it into the system, and there's no end to, when can we stop at some point and conclude that the theorem is not provable, is not true? The conventional propositional logic system has no real good mechanism to stop and say, okay, we have come to a dead end, this theorem is not true. Or it does not guarantee that you can always find a theorem that is true, because it all depends on how you apply the rules in zeta, in the transfer in zeta. These are the inference rules. So this is the wrong symbol to use. We're supposed to use z as zeta. Are we doing okay so far with the connection? Okay. Let me give you one specific example, just based on what is on the board here. This chair is in the way. Okay, so we have all of these axiomatic truths, and then on top of all of this, in iota, I also give you something that is not just the axiomatic truths, but I'm also telling you that, oh, you know what? I also know that P implies Q is true. In other words, if P is true, Q is guaranteed to be true. I know that expression to be true. Is that okay? Because just by this, we are introducing something that's new. All of these things here are axiomatic, which means we're just defining what the operators do. Okay, this one is not axiomatic. This one is specific to a particular system. I'm just saying that if I know P to be true, I know Q is true. Is it okay so far? And then I can also tell you that, oh, you know what? I know the negation of Q is also true. So I can start an iota with additional components like these. Is that okay?
Depending on the system?
Depending on the system, exactly. Depending on what you try to prove and what is given to you to be true. Okay? So in this particular system, I'm told, okay, it is given that P implies Q is true. It is also given that the negation of Q is true. So now I have to use these rules in zeta to try to prove a theorem. Okay? So let's say the theorem that I want to prove is not P. Okay? I want to prove that not P is true. So now the question is not P true or false? Can I prove that not P is true? So what do you have to do? You have to go through all the transformation rules, right? And then see what is applicable. But the problem is we have rules like these where it can keep expanding to stuff that is useless. Because from this particular rule, I can basically add to the stuff that is known to be true and say that, oh, you know what? From this, I know that P or not P is true. I'm adding this expression to everything that is known to be true. First of all, is it wrong? Is it wrong that this expression is always true? Whoops, this is supposed to be not P here. That's not the Q. Here we go.
No.
It is not wrong, but is it useful? It's not
depends.
useful. Well, in this case, it's not. In this case, it's not useful because it doesn't help us prove that not P is true. But I can keep using the wrong inference rules to keep adding new things that are known to be true. It is not incorrect, but it doesn't help me prove the theorem that I want to prove. In other words, to prove a theorem, even something as simple as this, it relies on the experience of the person who is using the inference rules and pick the right ones at the right time to get to the actual end result. That's the problem, okay? That is a problem of the propositional logic system. So the next question is, how does CNF help? Okay? First of all, can I convert this into a CNF?
Yes.
Okay, let's do this as an exercise. Okay, let's look at P implies Q and say, that doesn't look like a CNF to me because it doesn't even have a conjunction in it. Okay.
It's not.
Okay, it is the same thing as not P or Q. Is that a CNF?
Yes.
It is a CNF already. Excellent. Is that a CNF? Not Q. Yes. It's already a CNF. So not P implies Q is a CNF because we can convert it into this. Not Q is a CNF already. So if I just use a gigantic conjunction and say, okay, this is a CNF and this is a CNF, then the conjunction of these two is also a CNF. In other words, the notation or the format of a CNF can be used to capture everything that we did with traditional propositional logic. Is that okay? Because that's one important connection. So the second important connection is in the next slide. The next slide talks about resolution. Resolution is kind of mechanical, okay? Resolution basically says if you can find a well-formed formula, that has, in this case, phi or psi, you have another well-formed formula that has not psi or rho, then you can combine these two and say, oh, we can make a conclusion. We can infer that phi or rho is true. Do you guys have a question? Oh, okay, all right. So that's resolution. Resolution is this, okay? It's a transformation rule, but it doesn't. It has a basis as well. So to show that there's this particular inference rule is sound, which means it does match reality, I have to prove the following. I have to prove this implication is always true. So let me just stop here, okay? Because I do want to make sure that we understand what I'm trying to do here. This is an inference rule, okay? How do I know this is an inference rule? Which symbol gives away that this is an inference rule? It is not an implication. Exactly, okay? That little T symbol that is rotated counterclockwise 90 degrees is a giveaway that this is an inference rule, which means it is a complete syntactic operation. It is really just saying, if you can see something like this and something like this, okay, now you can also conclude that this is true. Okay, that's syntactic. But the question is it sound? Okay, because if a syntactic rule is sound, it means that it also has a matching truth when it comes to just the logic. And this part here is the semantic part of it. Instead of using a transformation or inference symbol here, I use implication. In other words, I want to find out in logic, does this guarantees that this is true? That's what I'm checking. So does everybody understand the meaning of why I have the inference rule to begin with, but since I want to make sure that the inference rule itself is sound, I also have to prove the semantic is holding up true as well. Okay? So now that we understand the why and also the what, the how is really just a whole bunch of details. I mean, this is exactly how I do this. You basically just say that this entire side is the left-hand side of an implication, so the negation of that becomes the first part, and then we have an or of the second part, just like that. And then since it's a negation, I convert, I can use De Morgan's law, okay, to turn the conjunction into a disjunction with the negation applied to the individual components. And then I apply De Morgan's law again into the inside of this thing. And then the other side, because a disjunction and a disjunction is associative, so that's why I can dissolve the parentheses on the right-hand side. And then over here, from here to here, I use this kind of tricky rule here. Okay, so let's take a look at this transformation or this particular derivation. So originally I start only with a phi, but then I can say, oh, if phi is true, so is phi and 1. Is that okay? Does anyone have a problem with this? Okay, it's not a problem. Yep, go ahead.
When you bring the negation into the parentheses, is that distributive?
No, that's De Morgan's law.
Okay.
Yeah, so going from here to here is De Morgan's law. You can kind of look at De Morgan's law as the distribution of the negation into the inside of the last operator, but then you have to remember to change the operator too. If you start with the disjunction, you end up with a conjunction. If you start with a conjunction, you end with a disjunction. Okay? All right, so go ahead. Any questions?
Oh no.
Not yet? Okay. Any other questions? Okay, so from here, okay, from this extra and 1, then I go like, oh, what is 1? What is true? Oh, we can just do that, right? We just talked about a little bit earlier using this particular inference rule, which is also sound, okay? I can say that doesn't matter what psi is, okay? Psi or not psi has to be true. Is that okay? And then the same thing with this one over here. I also, okay. So with this one here, I do exactly the same thing. I just say, okay, 1 is psi or not psi. I just need to scroll over a little bit. Just give me a second here to scroll, and then scroll back. Right there, okay. So now I look at this whole expression here and go, I see that I can apply the distributive law here. So this becomes that, right? Because I'm just, applying the phi and to the individual components on the right-hand side. So phi and in parentheses, psi or not psi becomes phi and not psi, and then phi and psi. Is that okay? Are there any questions about this particular transformation? Okay. And apply the same thing to rho as well. So this expression becomes these two expressions. Are we still doing okay so far with all this stuff? Yep.
Could you put those in any order?
What do you mean by in any
Could you
order?
put phi and psi or phi and not psi?
Yes, because they are commutative.
Okay.
Yep. So that's why this not side was originally here, but I moved the order. I changed the order. Okay. And then what I did was I regrouped things a little bit. Okay, so I regrouped so that we have okay, this part here is not obvious because what I did was to move this guy. Okay, I moved this so it's right next to this guy here. Then I reversed the distribution. So I simplified, okay? So I simplified so that not phi or phi becomes together, and then the whole thing and not psi. But this whole thing becomes just a 1 and something, so I'm left with not psi, okay? And then I do the same thing with rho. I basically put, again, just looking at which one we're dealing with here. So we have psi and rho. Okay, so basically I put this thing here right next to this thing here, and we can factor out the psi and then have rho or not rho to be on one side to simplify. But rho or not rho becomes a 1, so I'm left only with a psi. So now that I have a not psi on one side and a psi on the other side, this entire disjunction simplifies to true. And once I have one true in a long disjunction of stuff, then the whole thing is already true. And so this is concluding the proof that this particular implication, okay, that's not the entire thing. I have to scroll back again to the beginning. So the bottom line is I have just proven that this implication is always true. And that's using Boolean algebra, okay, using the semantics of the operators and not using the syntactic operation that we use in inference. So at this point, I have established that the transformation, which is this particular inference rule, makes sense. It is sound. Because I can prove that the equivalent implication is always true. Is that okay so far? What do you think is another way to do this? It's actually the first sentence of the second paragraph on the projector. Use a truth table, exactly. So in this case, how big is a truth table? How many rows are we talking about? How many individual variables are we talking about?
3.
You have 3, so you have how many rows? You have 3 independent variables. So when you try to prove something using a truth table, how many rows are we going to end up with? 8 rows. Very good. Okay, so you can use an 8-row truth table to actually prove this. Are we still doing okay so far with all this stuff? So this is resolution, okay? What I have just highlighted on this board here, this part here, that's resolution. But why is resolution so cool? What makes this more useful than the conventional inference rules? This is just an inference rule too, but why is this particularly useful? Okay, if you look at the what we need and what we end up with, let's just take a look at that and see what we're dealing with here. We don't start with nothing, okay? We always need to start with 2 well-formed formula where they share a quote-unquote share a variable. They don't exactly share a variable because on one side it has to be a non-negative version, on the other side it has to be a negative version. In other words, I cannot just apply this inference rule to anything, okay? I can only apply this when 2 well-formed formula in the CNF fits a particular format. That is good because it limits how often I can apply this inference rule. And then the second thing we want to look at is, okay, what about the consequent, which is the result of inference? Is it simpler or is it more complicated than what we start off with?
Simpler.
It is simpler because we started off with 3 variables or 3 things, and we only end up with 2 things. So the repeated application of this inference rule will continue to produce new things, but all the new things will contain less terms than what we started off with. Is that making any sense? Which also means you cannot apply this infinitely, because every single time you apply, the new things that you're producing has 1 term less than what you started off with. So if you continue to reapply this, you'll basically end up with fewer and fewer and fewer terms. So eventually you end up with one of 2 situations. I get you. So we end up with one of 2 situations. One is we conclude with a 0, which means, if you have a 0 in the entire CNF, the whole thing is false. We have to stop. Or 2, we can no longer apply this particular inference rule. We are at a dead end. There's nothing else to do. So we have to stop at some point. Yeah, go ahead.
So the idea is that we have a whole bunch of these inference rules?
We only have 1 single inference rule. That's the beauty of this inference rule is instead of using this gazillion inference rules, we only need 1 to prove theorems.
And do we just figure out which one we need, or?
No, we just need to figure out who we apply to. Which 2 expressions to apply the resolution rule to. That's the only thing you have to do is to choose, okay, this one and this one, one has the negative version of a variable, one has a non-negative version of a variable, then you can apply resolution. So the end result is kind of like a concatenation of of what you start off with, but without the variable that is negated on one side and non-negated on the other side.
I guess I was just under the impression that we had more in Zeta than just like more in
In this case, we only need 1 because this is the 1 rule that we need to resolve everything. That's the nice thing about resolution is you don't need all these other rules anymore. You just need 1. But it only works on CNF, and that's why we talked about CNF. Okay, that was a good question. Any other questions before we move forward and take a look at some examples? No questions? Okay. So we have a little example here. I just I assign certain meanings to P, Q, and R just to make it a little bit more interesting. So I just say P as a variable is basically the sky is magenta. Okay? It's a variable because it can be true, yes, the sky is in fact magenta, or false, the sky is not magenta. So it's a variable. Same thing with Q, all soy milk spoils, right now, okay? It's a variable, okay? Is it happening or is it not happening? And then R is a variable as well. At the end of the semester, does everybody pass this class? Okay, that's a variable as well. Because it can be true, it can be false. So P, Q, and R, they are variables. So now we start to establish certain truths in this system. So don't ask me why, but this implication is known to be true. Okay? In other words, we know that the sky being magenta implies that everybody is going to pass cisp440. Probably on some weird planet, right? And for whatever reason, don't ask me why, but this is also known and established to be true, is P or Q, which means the sky is magenta or all soy milk spoils. Is that okay? Because apparently somebody did not put in enough preservatives in the soy milk, so they all spoil. And then the last one is, we also know this to be true as well. Okay, it is not the case that Q and R. Okay, so Q is all soy milk spoils, and everybody passes cisp440. Those two things cannot happen at the same time. They cannot both be true at the same time. Don't ask me why. It's just that something that we are given with. Okay, so this is, in other words, these things are now in our iota, okay, because these things are known to be true, and just say, don't ask me why, we just know these things to be true. Are we doing okay so far with that? Did I tell you a single thing about whether the sky is actually magenta or not? No, I did not tell you whether all soy milk spoils or not, nor did I tell you whether everybody passes cisp440. Okay? So I did not state a single truth about each individual variable. I'm just telling you that these expressions are known to be true. So now the question is, I want to prove one way or another, okay? I want to know whether I can conclude and say that R implies Q. Can I say that everyone passes cisp440 implies that all soy milk spoils? That's the theorem that I want to prove. I'm not even sure whether it is actually a theorem or not. At this point, I want to prove it. Does everybody understand where I'm going with all this stuff here? Okay? All right. Oh, I guess I forgot to use one backslash down there. So the proof using resolution is basically saying, okay, can we derive it? Instead of proving R implies Q directly, we negate it first. So we are trying to negate the theorem, the very same theorem that we try to prove, we negate it first. And then we combine that with the CNF of whatever we are given with. And the mechanism to do this is over here. So we need to talk about the corollary first, okay, which is basically a small theorem that is important. So the first question is, can I make this claim? Can I say that if I know P implies Q, then I also know that P and R implies Q and R? In other words, is this statement true for all possible combinations of P, Q, and R? That's the question. What do you guys think? Does it make sense? Does it seem to make sense to you? If you know that P implies Q, can you immediately come to the conclusion that P and R, or some kind of R, implies Q and R? In a way, it makes sense, okay? But if it doesn't make sense, it's okay too. Even if it does not make sense at all, there are two ways to prove this, okay? And I think by now you should know the two ways. The easy way is going to be truth table, exactly. And how many rows do we have with this particular truth table?
4.
How many variables do we have?
2.
We have 3 variables, okay? We don't have just Q and R, but we have P and Q. R is the third one. So we have 3 independent variables, and it has 8 rows in the truth table. So you can prove it by truth table But we can also prove it by just the Boolean algebra, which is what I did down here. I actually enjoy the process, of proving it using Boolean algebra. But you can see that the common technique compared to the previous one is this thing here. Okay, the trickiest part of the proof. The first part is really nothing more than just transforming the operators, and I think I might have copied and pasted one thing here that is, yeah, this one is extra. It's not wrong. It just doesn't need to be here. But the trick that turned out to be really useful is this one here. You saw this earlier. Okay.
Introducing the one.
Yep, I just introduced an AND one here, and then I turn that one into Q or not Q, and then I distribute this whole thing, rearrange things a little bit, so that eventually I end up with 1 and not Q, and then we have Q and 1 here by recombining things, by simplifying equations. So that basically can combine into 1, because 1 and not Q is just not Q. Q and 1 is just Q, but now we have not Q or Q, which is 1. And once you have true or whatever, the whole thing is true already. So this is the conclusion of the proof that this does work, okay? But why is that useful? Well, let's see why it's useful. Down here, proof by contradiction. We talked about proof by contradiction a few times already, but it was never really formally introduced. Okay, it was never really formally introduced or justified. Why does it work? Okay, so what we want to do is we are going to assume that you start off with some gigantic CNF, and it implies the theorem that you're trying to prove. So in this case, in our application, psi is going to be the CNF of these things here. That's turn all three into a CNF. That's what psi is. This is the theorem that we are trying to prove, which in this case here is our phi. Okay, so we want to establish this. Okay, we want to say, okay, phi is the theorem that we want to prove. So we want this implication to hold true. But instead of proving this directly, we make use of the transformation of this thing here, because when you say that psi implies phi, it is the same thing as saying not phi implies not psi. Have we talked about this before? The answer is yes, but you might have forgotten. So let me show you how that works. Okay, so we'll use a notepad here to show that. Okay, so we start off with P implies Q. Okay, P implies Q is saying the same thing as not P, or Q. Is that okay? That's by definition, okay? That's the definition of implication. So I'll just add here and say by definition of implication. Okay. What can we do about this? Let's see. Can I do this? Instead of just saying Q, can I say not Q? Would that be okay? It's just double negation, right? It seems like you're doing this. This is nonsense. You're making something simple into something that's even more difficult. Okay. This is just double negation, or I should say the identity of double negation. Okay, the next one is going to be this. Okay, so we have not Q or not P. Would that work? Is disjunction commutative? Can someone prove that disjunction is commutative? How would I prove that?
1 or 0, 0 or 1.
You can use a truth table.
Yes, you can use a truth table again. So you can use a truth table to prove just about any axiom in Boolean algebra. Okay? All right. So this is using the because disjunction is commutative. Okay, there we go. Okay, can I do this? Okay, it's just using some extra parentheses, okay, it's meaningless. But given this, can I say not Q implies not P? Because it's the negation of the first thing implies the second thing. Isn't that the definition of implication again? Okay, so once again, we say this is by definition of implication. Okay, so that means P implies Q is exactly the same thing as saying not Q implies not P. Okay, but this alone by itself is not proof by contradiction. It gives us one of the components, one of the pieces, so that we can use proof by contradiction. Okay, so getting back to here, remember what psi is? Psi is a CNF of everything that is known to be true, that is given to be true. Phi is the theorem that I'm trying to prove, but since I can show that this is really saying the same thing as this, right? And using the corollary that we have earlier, which is basically saying if you can say that P implies Q, then P and R implies Q and R is also guaranteed to be true. So now we can say, what about this thing here? Okay, so we are now looking at not phi as, okay, what am I saying? Oh, okay. So this part here, not phi implies not psi comes from here. Okay, is that okay? Okay, let me see if I can. I'll just go ahead and point on the whiteboard. Okay. Forget about psi and just forget about that stuff here. Okay. Not phi implies not psi is a result of this, which we just talked about earlier. Is that okay? So that is established. And then I just attach phi and phi to it, okay? Which using the previous corollary, we can say that, oh, okay, you can attach a conjunction with something else, the implication will still be true. So now we have phi and not psi implies phi and not phi. But what is phi? What is psi and not psi? What is the second rule? Regardless of psi, what psi is? No. There's a conjunction here, not a disjunction. It is guaranteed to be false. So that's how we get the contradiction. Are we doing okay so far, or still need some more time to digest this? Okay, so maybe I'll just write on the whiteboard here. I just want to kind of stitch all the pieces, individual pieces that we have into, why do we know that proof by contradiction works? Okay. Psi is a CNF of all WFFs known given true. Okay. So these are all things in the iota. Okay. These things are all given to be true. Don't ask me why. Phi is the theorem. This is a theorem. So we need to prove it, okay? Prove it to be true or false, okay? This is a question, okay? Can this imply this? Okay, that's the thing. So I'm saying that if phi is really a theorem, then we know that psi, which is a CNF of everything that we know to be true, should imply phi. And that's the nature of a theorem, is it follows, it is a consequence of everything else that we know to be true. Is that okay? So far? So good? Okay. But we also know that another way to write this is to say, we can rewrite this as not phi implies not psi. These two are equivalent. If you give me one, I can conclude with the other one. Is that okay? We just proved this a little bit earlier. Okay? And then on the earlier in the notes here, we also have that conclusion. We say that if you know that P implies Q, then we also know that P and some R implies Q and the same R. That's what we proved, up there a little bit. Is that okay? Is everything okay so far? Okay. So how do we make use of this and this, and then prove, and then show that proof by contradiction as a technique works? It makes sense logically. Okay. We start with not phi implies not psi. Okay, that's because of this.
Is that our zeta?
Say again?
Is that our zeta?
You mean this part?
Yeah.
It's not. This is because of the assumption that phi is a theorem. If phi is a theorem, this has to be true. If this is true, then this has to be true as well. Is that okay?
So no. So the answer is no.
The answer is no. Well, we haven't got to the contradiction yet. Okay. So this R is the key key component. This R is the negation of the theorem that we're trying to prove, which is not psi. Okay? Is that okay? That's the theorem that we want to prove. We are combining the theorem that we try to prove into the system so that originally we have this. Our P is really psi, which is the CNF of everything that we already know. Q is the theorem that we want to prove, which is psi here. Is that okay? But because this implication is true regardless of what is P, Q, and R, now we can say this P is the same P, which is phi, which is psi, right? This Q is the same as this Q here, which is phi. This R is the negation of phi. Is that okay? So when you look at the conclusion, it basically means that if phi is really a theorem because of psi, then by introducing the negation of the theorem to psi, which is everything that we know to be true to begin with, we should end up with phi and not phi, which we also know as what? Zero, which is our contradiction. This is why proof by contradiction works. By introducing the negation of the theorem into the stuff that we know to be true to begin with, if this somehow leads to contradiction, then we have just proven that psi, the non-negative version of psi, which is the theorem that we want to prove, is true. Is that working or not? Okay, let's revisit the three questions: the why, the what, and the how. What you see on the whiteboard, and also the derivations, that's just the how. Okay, that's the mechanical stuff of how do we manipulate symbols in Boolean algebra. But what exactly are we doing? We're introducing a few things. Okay, we are establishing this thing here. We are establishing this thing over here. Those are the what, okay? We are dealing with proof by contradiction. Then the next question is, why do we want to prove by contradiction? Because if you prove by contradiction, you can use the CNF and the resolution. Is that making any sense at all? Questions? Okay, I'll give you one example of proof by contradiction. And I'll write it on the board too, so this way we have it recorded. Okay, so tech only has one kind of socks in the drawer, okay? So the question is, okay, I should rephrase this as a true-false thing, okay? Does tech get one pair of matching socks? taking any two socks from the drawer. Okay. So because I want to cast it as a true-false thing, so it's a theorem. Okay. Tag getting one pair of matching socks by taking any two from the drawer is a theorem. So the question is, how do I prove this? It makes sense to you, right? Because if I have only one kind of socks in my drawer, I should be able to pick any two socks out of the drawer and have one matching pair. It seems to make sense. But how do you prove it? How do you prove it mathematically using this logic?
So that first statement, tag only has one kind of socks in the drawer, that's your iota?
That's in the iota, correct. So this becomes our psi, which is reflecting what is given to be true. Is that okay? The theorem, okay, this is our phi, which is our theorem. Tag gets one pair of matching socks by taking any two from the drawer. That is my phi, which is the theorem to be proven. Okay? I don't know whether it's true or not. I want to prove it. Is that okay? So how do I prove this by contradiction? So the first thing I do is to negate the theorem. Negating the theorem means that I'm negating this particular sentence here. What is the other way to say that this is false? Instead of saying, double quotes, tag gets one pair of matching socks by taking any two from the drawer, end quote, is false, what is the other way to say this?
Tag get 0 or more than 1.
Tag does not get one pair of matching socks. Yep, exactly. The rest would be the same by taking any two from the drawer. Okay? Is that okay? So negating the theorem will give us the negation of phi. So now what I need to do is to say phi and not psi, excuse me, psi and not phi leads to false. Okay. All right, so let's combine these two. So we have this statement here as the given, which is psi. I'm going to use parentheses around it so that it's clear. And I'm combining that with the negation of the theorem, which is this sentence here. And I want to say, well, do we have a contradiction here? Well, okay, maybe not immediately, but what can we infer, not in the sense of inference, but what can we deduce, with this one single sentence here? Tag does not get one pair of matching socks by taking any two socks from the drawer. They're not matching, right?
Yeah.
The two socks are not matching. If the two socks are not matching, yes, go ahead.
But I'm a little bit confused. Does that imply that there exists two socks in the drawer? Because if there don't, then you could also have that statement be false, that tag gets one pair of matching socks by taking any two from the drawer. Oh, but then it'll be true because you can't take any two socks from the drawer.
Yes. So the key here is this particular statement. I took two socks out of the drawer, but I did not end up with a matching pair, implies that the two socks are different, because that's the only reason why I don't have a matching pair.
There exists two
Okay.
socks that are different.
So now I claim, so these two claims are now contradicting each other, because the first sentence, that states, because this is known to be true to begin with, tag only has one kind of socks in the drawer. Okay, that's given to be true. But because of the negation of the theorem, we came to the conclusion that two socks from that drawer are different. And these two are contradicting, because if I only had one kind of socks in the drawer, I should not end up with two different socks if I take just any two socks out of the drawer. So now we have something that is contradicting. So this whole thing ends up with basically false, because they contradict each other. They cannot both be true at the same time, and yet they're connected by a conjunction. Is that making any sense? I cannot say that I only got one kind of socks in the drawer, and claim that I take two socks out of the drawer and they're different. I cannot claim those two things at the same time. Yep.
So what you're doing is showing the negation is false.
I'm showing you the negation of the theorem is false, and this is what you do with proof by contradiction, is proving the negation of the theorem leads to contradiction, leads to false. Are we okay with the technique itself, proof by contradiction as a technique? Okay? Okay, so now we have these really kind of odd pieces here. So let me just restate all the pieces that we have and see if we can connect these pieces, because I think that's important for us to actually get to that conclusion today. We have propositional logic, or calculus. On one side, we talked about CNF, okay? Now, the connection between these two is using the techniques that we have just talked about. I can convert any WFF into a CNF. That's the connection between these two. Okay? Any WFF can be converted into a CNF. So that means CNF is kind of like a universal representation of everything. Okay, you can look at it as a canonical form of stuff. Okay, so that's CNF. And then we have resolution, right? So with CNF, I can apply resolution, okay, as a mechanism. It's just an inference rule, okay? It's very simple, but we only need one transformation rule, okay? So resolution as the only element in Z. That's the only transformation rule we'll need to know. Is that okay? Which is great, because instead of those 20, 30 individual transformation rules that I cannot remember, I only have one to remember. I can do that. Is that okay? So now we have propositional logic, we have CNF, we have the mechanism called resolution. So, and then we combine this with proof by contradiction. So we say proof by contradiction. So we combine all of these things. Now what do we have? We have a mechanical system to prove theorems that is guaranteed to terminate. That has to do with the fact that in resolution, you can only apply resolutions a certain limited number of times, and no more than that. Because every single time you apply resolution, whatever you end up with has one fewer variable. So if you apply that many, many times, then you end up with single variables. Then you end up with zero. Because what do you get when you resolve two things like this? Okay, but what if you have p or 0 on one side, and then you have not p or 0 on the other side? Can we resolve this? Does it fit the resolution format? One has the non-negative version of a variable. The other one has the negative version of a variable. They can resolve. But what is the result of this resolution? We take the rest of each expression, combine those two with an OR. So we end up with what? 0 or 0. Which we also know as what? 0. So that is usually the last step of resolution when you successfully prove a theorem to be true. But you have to introduce the negative version of the theorem into the whole thing first. Then you can use proof by contradiction and resolution and CNF to do the theorem proving part. So are we kind of connecting all the pieces at this point? I'll give you examples on Wednesday, okay? Or you can read ahead of me and actually read the examples. I'll give you a quick preview of what we'll be talking about. So we get back to the stuff that we talked about earlier. The first thing we do is we convert everything into CNF. CNF, CNF, and CNF, okay? And then we negate the theorem that we try to prove, which is this one here, but by negating it and converting it into its own CNF, now we have 4 components in the large CNF. And then what we do is we look at these 4, okay, as one gigantic CNF, and say, can we resolve this all the way to false? That's the question. Can we resolve this all the way to false? And when you follow these individual resolution steps, then we are stuck at this point. Okay, when you look at this expression here, when you look at this gigantic CNF, you can say, well, we can apply resolution, but we won't come up with anything new anymore. That is the whole point. You can reapply resolution all you want, but we are not going to end up with anything new, which means we are now at a dead end. And yet, we are not getting to the conclusion of false, which means the theorem is not true to begin with. We cannot come to a contradiction. Okay? So with example 1, the conclusion is R implies Q is not a theorem because we got stuck in the process. In example 2, okay, we are trying to prove R implies R implies P, and when in this particular process, you can see that we quite quickly arrive to a conclusion of false, okay, by resolving this R with this not R here, we end up with a false, and as a result, because the negation of the theorem results in a contradiction, results in false, then we can say that the theorem itself has to be true because of the technique that we today Today we introduced a technique called proof by contradiction. So is that okay? I mean, are we getting the big picture? Okay, the big picture is important because once we understand the big picture, it's easier to navigate the little detail. It's just kind of like planning a road trip. It's important to identify the key points that you want to visit, and then you just connect the smaller dots together later on. Are we good on this? Okay. So I will come back to this and actually show you example 1 and example 2 on Wednesday. But you want to read the notes, at least up to this point, so that on Wednesday when we talk about this, you guys know the mechanism well already, and also know all the the answers to the 3 questions well at that point. All right. So I'll see you guys on Wednesday.